So today we're going to go on with connectors. This will take probably a couple of days. It's a pretty long topic. There are a lot of connectors, and we'll look at a couple of examples of how to actually do the calculations, which gets a little bit involved. And I thought, well, okay, I'm not going to get through it today, so I really couldn't, even if I did get that homework made up, I wouldn't want to give it to you this weekend. And if I give it to you next weekend, it's kind of back to back with your preparation for what you're doing in here. So I think we're going to cancel the last one. Sorry, I know it's a huge disappointment, but we are all done with the online homeworks. We'll stop at 10. Okay, but we will mention one more wood of the day. At least we'll do one today. Hickory. I mean, how can you not look at a sample of hickory? Mark Kresick gave this to me a few years ago, I guess, and claimed it was definitely hickory. It looks a lot like the ash, but it's not. It's hickory, and you can feel from it. It's a pretty dense wood. This one's pretty heavy. I'll let you inspect it there. And hickory is one that gets, I guess it's not too often used for construction. It's used primarily for tools and I guess farm implements, things that have to carry a heavy impact. What do they make baseball bats out of? I think is that hickory? Good question. We should look that up. You check that out. See what they make baseball bats out of. But I know they make a lot of tool handles out of it. It has very high impact resistance. I think this says it grows all over the eastern United States, but we tend to commercially harvest it mostly in the south. It is a lighter color, as you see there, although the heartwood can be a little darker. It is, let's see, very sharp. It comes in two grades, basically, depending on how, what the growth situation was. If it grows real fast, it's less dense. The rings are a little wider spaced. If it's from a more slowly grown tree, I guess, it's much more dense, and so there's a distinction that they can, you can observe it by the density of the rings, I guess, when it's cut. And the higher, denser grade is what they use for tool handles, and that's one that's usually used. It says it's used for a lot of athletic equipment. Rungs on ladders. Okay, yeah, I guess that could potentially have an impact, right? Those rung on ladders, if you slip, you don't want to break your thing you're standing on, so that's often hickory, apparently. Right. And the lower grade, the other thing they usually avoid are samples that would have a higher number of knot holes in them. So usually, that's the last thing you want in like a tool handle or something, is a knot hole. So there we go. There's our hickory. Here you go. For all of you people in wherever you are, I don't know if that really shows up on the video, probably not. But that's hickory. Okay. And what else can we talk about? Connectors. I should have brought up, I have a pile of Simpson Strong Ties literature, and the pile I have is literally this thick. They have so many, unlike every and this is just, they sent me this one time. These are all from Simpson Strong Tie. They're samples of their fasteners and connectors. they have a huge array, and they have literature that covers all of it. And in terms of actually specifying the support, this end of it, you have to go to their literature. They're usually provided with ample nail holes. Of course, that we'll see how you would calculate the strength of those nails or screws. But the actual strength of these, I suspect they usually, something like this, they design it to carry what would be the maximum load for the joist size that would fit in here. You know, and give adequate bearing for what would be conceivably the maximum load that would. So usually that's not the controlling part of the design. It's the wood side that would control. You can see there are large arrays. Some of them we've looked at already. Oh, I forgot to turn my. Oh, yeah. Well, looks like it's going to work. Looks like it's even. These are the tie downs for the shear walls that we talked about earlier. This is a spacer in a panel that provides, I guess it should provide, I think that's supposed to be an 1/8 inch space in there. So that would be like on a diaphragm or decking roofing. You can use those, and I think I've even got one in there. Look at that. They give it support so that it, actually I think that's mainly intended just to place it, because then you nail it down to really support it. So it's not like it, but it does, maybe on an unsupported edge that would give a little more, you know, one that doesn't have blocking. That might be a solution. You can see here they're very, I don't think I have a sample of this one, which I'd like to get. They raise it, this is for a column, right? And it's raised up off of the base to prevent moisture penetration into the wood, which is a real clever design. So it's fastened, you know, bolted down to the concrete underneath it, and then you put the wood on top of it, which is kind of a nice design. Anyway, we'll talk a little bit about those. Generally, in terms of what you're looking for in a wood connection, of course, strength. I mean, obviously you have to have the strength to transmit the loads, but and that's usually pretty easy to attain, but what's more, maybe more of a consideration with the wood is the ductility. You could just connect something like this with just one giant bolt, right? That would be almost what you do with steel. Steel, you have these 3/4 inch or larger bolts, and there may not be that many of them. There may be 3, you know, sometimes only 2, and that's adequate, because the steels that it's connecting to is probably a little bit stronger than the bolts. What's a 307's only like, isn't that less than 36 KSI? Maybe they're 35, I forget. Anyway, they're about the same strength. They're both steel. Whereas this is much, much weaker. So if you have a big steel bolt, it's obviously just going to crush the wood or split the wood. The wood wouldn't be able to withstand that concentrated load that a single bolt would put on it. So to get the ductility, you have to have lots of fasteners. That's what these plates like this are about. They actually, this is one, I mean, you look at the back of it, I almost hate to pass it around because these are sharp. But this is a truss fastener. And you can see it's got, I mean, probably 100 little fasteners in there. They're not very long, but they grip it, and they spread that load out over the wood, so the wood isn't as likely to fail. It spreads that load out, and the steel can be pretty small and still carry it. So ductility's very important. Yes, of course, ductility in any connection gives warning of the failure. You don't want a sudden, yeah, if you just had that one big bolt and it failed by cracking, that could be fairly sudden. Things crack and go, you know, but you want something that's going to slowly kind of sag. You want that deformation to give you indication that something's going wrong. So the things that we design, yeah, of course, the size of the connector, the number, the slenderness, spacing, end distance becomes kind of critical because if you get too close to the end, it just rips out of the material. You know, that's not, I mean, that's also a consideration with steel, but you can get pretty close to the end and not rip it out. But with wood, because it's so much weaker than the fastener, you've got to pay attention to a larger end distance, and that's we'll see it's proportioned by the diameter of the fasteners. Okay, so these are different examples of connectors. Nails are pretty common, right? They're low strength. They have a high ductility. When a nail fails, these are, I think we've looked at these before. These are different nail sizes. Did I pass this around before? I think so, right? Did you see? You do? Yeah. Okay, well, I'll pass it around to you. But you can see here that this, what we call 10 penny, I used to think it was a penny weight, that it was based on weight, but that's not where it comes from. It comes from the cost of the nail. I guess in England at one time or other, they actually cost 10 pennies for not one. It must have been probably a barrel or a box. I don't know how many were cost 10 pennies, but however many you were buying cost 10 pennies, and that's how they were. That's where that came from, and I guess it was by weight. You must have been buying it by weight, I suppose. So it translated to the size. So that's become the size nomenclature for it. Some of them, you can look at this ring shank, have rings that prevent pullout, and also the different. Some of them are galvanized. I don't think I have any stainless ones. If you have a stainless one, it's very smooth, and that even gets a reduction factor because it's more likely to pull out. So that the strength is not so much in, you're not going to break the steel. You're going to either pull it out, or what also happens, if it's in a connection that's like this and shear, it'll actually bend the nail, and the nail, that's what gives it a good deal of ductility. The connection ductility is that you have to actually go through bending that nail, and if you've got 10 of them, that takes a little bit of force to bend it, and as it bends, your joint displaces, right? So suddenly, you know, you see the deformation, and you've got some idea of the that something's gone wrong. Okay, here you go. You can pass that around and see the size of the nails there, different ones. This is of course a bolt, right? You can see it pretty hefty. That would concentrate the load. They are still used in connections, hopefully not just one, but you may have, I mean, I think the example I do is with bolts, if I remember. So that's one. These are called lag bolts. I guess they call them bolts because they have a hex head on them as opposed to a screw, but they are threaded. These are also usually larger in size than a screw and would be, you know, a stronger connection. But again, you have to have a little bit of caution. You can't just use one. You've got to, the idea is to spread it out. And you can see here, oh, the other thing that gets used sometimes are these are rivets. And they get shot into the wood with that pneumatic gun, I guess, on a plate. So that's another form of attachment. They're essentially nails, but I guess the difference is how they're driven in. This thing up here, this is an example of a split ring. These are used in truss construction, sometimes they're a little bit, I mean, probably have been replaced mostly by the gang nail plates, but on a heavier truss they'd still be used. Maybe if you had a timber truss where they're higher forces and bigger members, and you what you have is you've got that ring is embedded in the wood. It's, you know, not so thick that it cuts clear through the wood. It's like halfway through. It's in here, embedded in the wood, and so you have to cut that groove through it, and then it's through the center of it you get a regular bolt. So there's a bolt through it and the ring around it, and the bolt holds everything together, but the ring is what transmits the shear force, and that gives you a much larger, I mean the bolt's only like this, but the ring is considerably larger, gives you a much larger surface area, bearing area, and to transmit the load. So that works a little bit better with the wood. But you can imagine they're a little bit expensive to, I think we looked at these. Didn't I have these in a different lecture? I forget. Anyway, they're a little bit more expensive to install because you almost have to have a drill press to do everything. So it's almost like a fabrication shop would do it like that. Probably not on site. Right, so wood is pretty strong parallel to the grain. We've seen that. I mean, you can look in the, in the NDS and immediately see, when we do the compression parallel to the grain, even in flexure, the stresses are parallel to the grain, right? And in tension, of course, where you get tension, tension perpendicular to the grain, it has a very, very low stress. Do they even give that in the NDS? I guess they do. Let me see. Just as a comparison here. No, they don't even give tension perpendicular to the grain. You're just not supposed to do that. They give compression perpendicular to the grain. That would be, like this would be in bearing. Okay, that would crush into the wood a little bit. And you remember when we did those end bearing things, it's based on crushing distance, actually. But actual tension like this is to be avoided. They don't even, at any rate, they don't give us stress even for that in here. I thought they did on, maybe they do on glulam. Seems like I'd seen it somewhere. Tension parallel to the grain. Shear parallel to the grain. No, I guess they don't. No, you can't even get that. Okay, so don't do that. That's kind of to be avoided. So this would be a good connection here because they've got the end supported. This is the steel coming out that's got it on it actually sits on it. So it's being loaded directly parallel to the grain, being loaded, the grain obviously in this direction. And that would be better than if you had just the bolts alone. Okay, that's still loading it at least in bearing perpendicular, but might split too. Okay, the other, in terms of splitting, one large connection, if you just had one big bolt here, it would be much more likely to cause splitting than a series of smaller fasteners. So this is, you should always try to spread out the load. It's also, because wood is it's organic, right? It has things like knot holes in it, and if you design a fastener that's going to just have one connector, you can't guarantee in advance that you're not going to come down right on a knot hole or right next to a knot hole or next to a split, right? You could be landing that one fastener in a not very strong spot. Whereas if you've got 9 of them like in this picture, okay, if one lands on a knot hole all right, so you've lost a ninth of the strength, but not 100% of it, right? So it's much more, it spreads out the load, it's more ductile, it's more, okay, it can act better in that regard as well. Okay, so here are a few that show some of this. This is a truss. I don't know where this came from, but I think it was in some of APA's literature. Probably not a good example because they have single bolted connection here. Maybe this was done with, to give them the benefit of the doubt, maybe those are split ring connectors, in which case it wouldn't be so bad. So, okay, maybe they are split ring connectors, but if it was a single bolt, that would definitely not be a good connection because it would be concentrating the load. These would be better where we see multiple fasteners, right? And the wood supported, you know, here's the one I had talked about earlier. This is actually more of a tie down, right? But it's also the support is resting on a little steel plate that raises it up off of the concrete. So that's the other consideration. Okay, these are some other ones here that help to, you can see just multiple fasteners, right? And the wood is not really, those fasteners are holding it in place and preventing it from slipping out that way, but it's really being held, the majority of the support load is resting on that bracket. So you can see there are lots of them that do that, you know, these that are made specifically like this. These are all Simpson fasteners, things that brace, that would be the corner. Here's one that isn't like that. I guess this is one that would be, you know, for a multiple depth, or maybe, I don't know exactly what the situation is, but it doesn't have the bracket underneath, so it would be holding it just by those supports. That would be maybe, you know, that's kind of a special case, that's not too common. Okay. And of course, these, which is now the standard way to fabricate trusses, is with this gang nail. I forget. There was a guy who invented this. His name was not gang nail, but it was, I forget what his name was, but he had the patent for it, and then I think he sold it to Simpson. They bought him out, and I think they're still called gang nails. That was what he originally named them. They before these, they used to have plates that were just steel plates with lots of holes in them, and you'd nail through that. And before that, I mean, I can remember, actually, I showed you that house we built with my parents. I built another, we had to have a whole separate shed to hold wood to supply these fireplaces that my father was convinced had to keep burning. And I built the shed and built the trusses, and at that time laid the trusses out and had plywood gusset plates. So essentially this same thing with plywood, nailed through. And one technique to get a little extra strength, you have a gusset on both sides. You nail all the way through both, and then you flip it over, and it's called cleating. You bend the nail over. So the nail goes through, you flip it, and then you bend it over, and that's called cleated. And there is actually a provision in the NDS for the added strength of a cleated nail, I think, somewhere. Reduces the pull-out, I suppose. Anyway, but that's a lot more work than these. These, they place them, and they're all fabricated. There's a plant over in Ypsi that makes these. You lay out the wood on a big table, put these in place, and then there's a big hydraulic press that comes over. You know, they position it, and it stamps it. And they just go around and stamp them in. And they're, that way they go in completely. They are intended for tension and compression. This was actually a test that some students in here did. They did do one, I guess, in tension, and then just to compare it, they did this one in flexure. It didn't hold very much in flexure, and what happened is it just ripped up the side of it. It tore the connector. But it still did have I guess I could probably stand on it. It has still a good bit of strength and a lot of ductility in that failure, so wasn't really so bad. But they're not intended to carry flexure loads, I don't believe. Okay, in the NDS, here we go. There are 4 chapters that deal with connectors. The first one, 11, is primarily an overview, and this is where a lot of the, what do you call them, the adjustment factors are found in here. So some of them, but not all. The list of which ones you even have to consider are probably in there. They have that table like we saw earlier with all the factors and the different. We'll look at that. There's a later slide with that. This is the big one. Chapter 12: nails, screws, bolts, and pins. Those are the primary, what they call dowel connectors, and that chapter has a ton of tables. Where is it? Is this 12? Yeah. These are probably all the list of the tables. Yeah, I think they are. Those are all tables that give design values. So you'll see when we go through it, the calculations can be pretty complex because there are a lot of different modes of failure, and you have to really do a calculation for every mode of failure, and that gets to be pretty detailed. So it's much well, not just easier but more accessible is to use the tables. Of course, the downside of that is if you're trying to do it with a spreadsheet, it's a little bit difficult to plug the table into the spreadsheet. That's why my last homework has never actually been completed, because I can't use the tables, and just have never gotten around to actually creating that spreadsheet. Anyway, so yeah, most of this design, I guess, is done with the tables then. These 2 last chapters, split rings, we mentioned those, they're kind of specialized. So there's a chapter just on the details of split rings. It's not really too long. And also one on the timber rivets, which, again, are kind of specialized. It's also more commercial. Although, I don't know. I guess those could be used on site more than the split rings are. I forgot to mention, speaking about on site, remember I mentioned to you there's a big wood construction light frame project off of Depot. If you drive down Depot, going out of town, just past the train station, you look up on your left, actually it's one road above you. If you went to the parallel road up there, they're doing it like an apartment building. It must be 4 or 5 stories high. It's all light framing, and right now it's all sheathed in this. And from the road, I thought this was that what do they call it, the sheathing board, not the OSB and not plywood, but there's a third option. I think it's just called shearboard, or I forget the name of it. But remember in that video I showed, the fellow mentioned it, and he kind of, yeah, it's like cardboard. I would never use this. So I kind of thought, oh, that looks like that's what that is. And I went up there, and it's not. It's all OSB. They gave me a sample of it. This is like a really heavy-duty, although this one, it's losing a little there, moisture barrier, waterproofing, essentially. So on the outside, which is getting soaked right now, it's got this on it. So hopefully, mostly on the inside, it's not too wet. But I guess that's probably a big reason you'd use these, is if you think it might be raining during the construction process, if you get this all soaked with water, that's really not too good. I mean, several days of water, it would not be good. But I guess this protects it. At any rate, it's getting soaked out there. You can see it. But it's kind of an interesting project. The guy was really nice guy. I talked to him for a little bit, and he gave me that sample. But they have I mean, you can see the entire thing is light framing. All the joists are, or all the beams are wood trusses, like a W truss that they've got in there, flat trusses. And yeah, it's pretty amazing. So it's pretty tall for you would think, well, maybe that's the limit. 3 stories is the limit for light framing? Because there's a fire code limit to it. I'll have to look that up. That would be in the IBC. But anyway, interesting project. I mean, you can see a little bit of it if you just drive by. You could talk to, if you go earlier in the morning when they're not real busy and tell them you're a student studying wood construction, they'd probably let you go in. They'd probably give you a hard hat and you could maybe look around a little bit. Okay, anyway. Yes, this is the table of service factors, the adjustment factors. And you can see they are separated by the types of loads. So here we have lateral loads, right? That would be kind of what I was trying to model with this. That would be where they're pulling laterally, like this or something, pulling. Withdrawal loads is where it's pulling out. So withdrawal would be it's nailed this way and the load is that way. So those would be withdrawal, pulling it out. So that would be like, studs that got an uplift load, right? Those would be in withdrawal. Or even the top plate, with a roof load giving it a section, that would be a withdrawal type load. Yeah, and then the pull-through. Pull-through is the last one. That's where the nails, that would be on sheathing. You've got nails on some sheathing, and the sheathing the nails stay in, but the sheathing rips through the nail head. And that becomes then critical, how big that nail head is, right? That would be why you never use finishing nails in construction like this, because they just pull right through. You want that head to hold it down, prevent the pull through as much as you can. Okay, so there are a ton of our old friend, the load duration factor, of course. That's exactly the same as what we've seen. The wet service factor is in there, but I think it's calculated a little bit differently. I believe there's a separate table. Temperature factor is probably pretty much the same, but there may also be a separate. In this chapter 11, some of the factors that apply to everything are actually given. There's like a little paragraph for each of them. Group action factor. This, as I remember, is a much more complicated one. That's a big formula, and then there's actually a table that lets you find it. But that's the accounts for the grouping of a lot of factors. The geometry factor is also, that geometry factor has to do with end distance, how close the fastener is to the end, and that end is specified, and if you don't meet that specification, if it gets too close, then you have a reduction factor, and that's part of that. That's what the geometry factor is, I believe. Penetration depth factor. Okay, I'm not even familiar with that. That only applies to split ring connectors, apparently. All right. So some of them you can see don't apply to just everything. But most of them, except for that one, and the, what's this, metal side plate factor. Okay, obviously that goes with metal side plates. That would be with the timber rivets. And shear plates, I guess, on that. Okay, but not otherwise not. Diaphragm factor, that's another kind of special. These are a little bit specialized, obviously, only for a diaphragm. Toenail factors, if you've got a toenail situation. Okay, so that's the overview of the factors. This is where it is a little bit different. This looks pretty close. I mean, it's the same sort of the ranges. I'd have to actually compare it. Maybe these numbers are a little bit different than they must be a little bit different factors, but also otherwise for temperature, there's those reduction for high temperatures. This is exactly the same. It just says specified in chapter 2. Okay, so those guys we're familiar with. The wet service factor is a lot more complex than for regular dimension lumber. First, you've got it by different load. All right, whether you got lateral loads, withdrawal loads, or pull-through. So it's broken into those categories. Then you have to look at the moisture content at time of fabrication versus in service. And this is because it makes a difference if it were, for example, if it was fabricated as not dried, not kiln dried, maybe it's a green timber or something, and then you drill the hole in it or you nail it or whatever you do, and then it dries out, then it really gets dry. Well, it's going to shrink when it dries, so that hole gets bigger. So suddenly your connection is loose because of the drying. So that would be, see if we can find that situation. That would be at time of fabrication greater than 19%. That would be wet, right? So there's wet. And at in service less than 19%. So this would be dry. So then you get this enormous, you're losing 60% of the strength in that case. Whereas if it were dry when you made it, and it stayed dry, right? Oops, that's supposed to be dry. Then there's no reduction. That's fine. And this is a little bit questionable when you make it apparently, and that is wet, right? This is wet when you. Man, I think it's the angle I hold this pen at. I have to be careful about that. Wet when you do it. Then there's a little bit of a reduction. That's not quite as bad as wet going to dry, but dry going to wet is not quite as bad. So anyway, so you have to pay attention to that and pick out which one applies. This is a little illustration that the APA, I think, had this in one of their brochures that sort of illustrates that it's the same as that other table. So this is the in service, at fabrication, and this is in service. So this is dry down here, right? And this is the wet up here. Okay, so if it's dry, then you're good. If it's dry wet or dry, okay, that would. Oh no, I'm sorry. This was the one that was either or, right? It was any, I think is what they called this. Dry or wet, but then wet. That was the one that was 0.7, right? That was what we looked at 0.7, and this is the bad one. This is where it goes from starts at wet, right, and gets dry. That's the one that you've got to be careful about. That's got the, and then for that same one, normally that's the value there, 0.4, but it has this little asterisk on it. I think that's footnote 2, right? That's what this is about, footnote 2. So here's footnote 2, and what footnote 2 is about is this. You can, even though it's done like that. If you meet this one of these criteria, then you can still take one. So if you've only got one single fastener, why that is, I'm not make a lot of sense to me, but somehow if you've designed it for a single fastener, that would get you back to one. If you have two or more fasteners and they're just in one single row, that would get you okay. If you have more fasteners but they're not joined together, that's not a continuous plate that joins them, or this would be not like a double row in here, because this is a single member. It would have to be, well, at any rate, the fasteners have to be, I mean, this, if there's like a steel plate on it, they have to be separated so they still act as a single row. So I guess that has something to do with the slippage in it. But if you meet that criteria, then you can, one of those three, then you can go back to one. So I think the main thing is just try to avoid this if you can. Avoid that situation where you fabricate it wet. Don't use if the connections are going to be critical. Okay, here's the, oh wow, this is my favorite, the group action factor. Look at that guy. And I didn't even, there's a whole nother equation that gives you M. That's, I don't think I can even write that out. It's, oops, 11. Where's 11? Seems like that was a, yeah. Oh, yeah. M's another equation that includes U, and then there's a third equation that defines U, which has a gamma in it, which is defined by, I mean, so you can see you've got a good 10 minutes of calculation just to get that. Or there is a table that gives this. I think maybe, hopefully, I don't know, maybe I didn't show it, but I'm pretty certain there's a table. 11. Yeah, there are several tables that define this. 1, 2, 3, 4 different tables, and they then cover the different combinations. They cover different areas because it makes a difference, the area relative of the top wood and the connector wood in here, the two different layers, and the size of the connector and the number of the connectors and the E-modulus system. So these are different tables that kind of let you pick it. So that is the group action factor. Then the other one, this is our the delta geometry factor. Here, this is about end distances, right? And if you meet these criteria for the different, perpendicular to the grain, parallel to the grain, and tension, then if the end distance is like 7 times the diameter of the bolt. So if I've got a 1/2-inch bolt, right? And I'm going to use these 1/2-inch bolts. Then the end distance, the end distance here has to be at least 7 for the softwood, 7D. So that would be 7 times 1/2. So for my bolt of D equals 1/2, right? That would be 3 3.5, right? 3.5 inches. I'd have to have that end distance of 3.5 inches. If it's a 1-inch bolt, you're going to have 7 inches. If you can't do that, sometimes there may be, because of limitations of the whatever constrictions, you may end up with less than that. If you are less than that, if you are, say, 3.5, if you can at least meet, if you can meet 3.5, then you use a factor of 0.5. So it looks like it's exactly cutting it in half, right? That's exactly what these do. The distance here from 4 to 2, 4 to 2, 7 to 3 point. Okay, you're cutting the distance in half. Then the factor cuts in half. And then there's a paragraph in chapter 12. This is in chapter 12, I guess. There's a paragraph under it that actually gives an equation for this, doesn't it? Where is this? What is that? 12.5? 12, all right, 12.3, 12.5, okay. Yeah. Here we go. In section, this is in the NDS, in section, I guess it must be 12.5, yep, section 12.5, they give a whole several pages, right, 2 pages describing this geometry factor, and they actually do give an equation for it, which is based on the base value here, right? What they specify in this column. So you can adjust it, whatever you have. You can kind of interpolate and get other values. But that all has to do with that connection specifically with the situation where you've got this end distance, right? That's the end distance we're talking about. Okay, so let me see, what are we up to? Withdrawal strength. Okay, this is in chapter 12. As I mentioned, there are a whole series of tables. These are the tables for withdrawal strength. There are tables not just for withdrawal strength, there are other tables as well. In fact, there are more tables for the connections like this, whatever you call those, parallel to the grain. But the withdrawal strength table, there's also probably the best or easiest to read table on specific gravity, because specific gravity comes into the connections a lot. And the specific gravity of the wood, they give it in the supplement, but there's one table that gives it all the specific gravity numbers, so that's kind of convenient, I guess. And then, where is this withdrawal? Here we go. These are the withdrawal tables. So there are, I guess, several of them, depending on the, like it says here. Table A is lag screws, threaded wood screws, smooth nails, smooth stainless steel nails, which, as I mentioned, have a greater tendency to pull out, ring shank nails, which are those ones with the rings on them, and then the head pull-through criteria. So there is a table for each of those that you don't really have to calculate them. They give you the values out of the tables. But just for fun, we can calculate one. This is an example, a simple example of pull-out. I think this came out of this, from the illustration, it looks like it's Breyer's, out of Breyer's textbook. He's got some nice examples in there, several chapters on connections. And this is, of course, we've got a downward load, right? And we'll just use a dead load on this, so we have that W of 0.9. It's just, this is supporting it, and so you can see it's just got a straight pull out right through this nail. The nail is a 16 penny. Ooh, hey, do I have a 16 penny? Where'd my nails go? It's got to be a pretty big nail. 16 penny, yeah, that's this big guy here. Oh, that's galvanized. Well, that's okay. 16 penny nail. And there is a table in here also, which we'll look at in a second, that gives all the specifications for the nails. Gives for every penny, it gives the length, gives the diameter, gives the length of that tip, which sometimes I think you're supposed to subtract off. So it gives all the dimensions of the nails. Those are all specified. Okay, so we can, for our 16 penny nail, where is he? 16 penny, looks like he's 3.5, right? It's 3.5 inches. This is here 1.5 inches, right? That's a 2x8. So what's left over is 2 inches. So my penetration, the amount that's really holding into the wood, is only 2 inches long. So I'm going to calculate this per inch. The calculation is strength per inch, and then we'll just multiply it by 2 inches to get the strength per nail. So there is, it's in the appendix. Is that where that is? There's the table. Gives me the diameter, gives me the total length, which I got from that nice little drawing. So my penetration, as I said, is 2 inches. Okay, I can look up the specific gravity. All right, and the withdrawal strength comes out of a table. Okay, I thought I actually had the equation there, but maybe I'm just doing this. Let me see what we got here. Okay, so here's the this is the appendix table. There's quite a bit in the appendix of the back here on connections. Yeah, and that's one of the things, that's nail sizes. Okay, so that just simply gives me the size. All right, and I guess I did just go to the table and pull out the strength here. So this is for, okay, specific gravity was, I think, Southern Pine. Is that what I was using? 0.47. Okay, 4.47, right? Okay, so that's that. And my diameter is 135. Okay, so that's that. And that gives us then 28. And I had to be in the right table. This is the table for smooth shank, either bright or galvanized. Okay, carbon steel nail. These are, the values are in pounds per, okay, pounds per inch, right, of penetration. And right, and the specific, so the wood is specified here, and the nail is specified on the top, and we've got it then. So 28 is it. Okay, 28 pounds per inch. I've still got to put adjustment factors on this. I haven't done that yet. So this is just the raw number. I've got to put adjustment factors on it, and I've got to multiply it by 2 in this case, because I had 2 inches of penetration. So to get at least the strength per nail. So that's what this was. There's the value out of the table that I just got, and the penetration is 2 inches. So that gives me the strength per nail, right, is 56 pounds per nail. And now I've got to put these adjustment factors. So this was the dead load. This is, I've got to figure that one out. Where'd that come from? And this, there's no temperature and no toenail. It's not toenail. Okay, so those we don't have to worry about. This one, the moisture. Let's see if I had I think I showed that. Ooh, golly, moisture. So first off, we've got withdrawal loads, right? This is the one we're looking at, withdraws. We've got nails and spikes. Okay, we got that. It was, look at this. Oh my goodness. Fabricated green. Okay, so that would be, this is greater than 19%, so this is the one that's wet. And I think the idea is it's supposed to be dry when I'm finished, right? Somewhere it probably said that, use dry. Okay, so fabricated green, use dry. So that then is my dry, and that is my, so there's where the 0.25 comes from. Did I use that? Yeah, that's that 0.25 right there. And footnote 3, always good to read the footnotes, is for roof sheathing ring shank nails. Oh, okay, it's not a ring shank nail, so that's out. Too bad. might have gone back to 1 if it were ring shank. A reason to use ring shank nails, I guess, but that's only on roof sheathing anyway. Okay, so that's it. That cuts me down to 12. There are, I think the idea was there were 6 of these on each side. So 6 on this side, 6 on that side. 6 times 2 is 12. And that gives me a total of 151. So the strength, I guess if this, maybe they're making a chin-up bar, I don't know what this is supposed to be, but it would hold 151 pounds. That would be about it. Right. And, you know, you can see where you lost most of it, at least in this example, was right here. You lost 75% of it right there. So you have to pay attention to, you know, doing it with green lumber is probably not, if it can be avoided, would be better. Okay, and now in patterns of connections, we look at 2 different things. This is a situation, I think, like what I was trying to describe with this. I don't know if I can pick this up. I should have nailed it together. But this is supposed to be a connection that would be pulled in tension, right? I'm just trying to show you. It's got the pieces top and bottom, and then a plate in the middle that's connecting the 2 pieces. So that's that would be potentially a tension connector, and in that we presumably have a pattern of bolts here, right? Not just one. That would be not what we want to do. We don't just want to have one. We maybe just have a row of them, but probably, depending on how big this is only a 2x4, but you could have a pattern. And in the, this is the appendix E, apparently they give 3 different modes of failure, right? They give, this is 1, net section in tension. I think that would be breaking across like that, where the thing would just tear in tension. The wood would actually break. A row tear out capacity, which would be just the rows tear out individually, right? And then the last one, which must be on the next page, is group tear out. And that's what this illustrates, is group tear out. Group tear out means the whole thing failed like that. And I think that's sometimes called tongue tear out, isn't it, or something like that. Anyway, with this they call it group tear out. That is controlled by the pattern and the spacing. In this case, this illustration was an example where they had the spacing very close together, and it kind of promoted this. It made it worse, made that group tear out worse. So normally, you don't want that. That's a no-no. Try not to have them too closely spaced. You space them out as best you can to fit across the width of the wood, and that avoids that a little bit. So you can see each of these scenarios will have a different calculation that goes with them. You have to calculate each one, and then you take the least, right? The lesser of the 3 would control, then would be the strength that you'd have to go with. Here we go. Here's the group tear out. So, in fact, this shows all. This is the row tear out, right? This is row. Man, that's supposed to say row tear out, and this is the group tear out. okay, is that one. And then the other possibility was the tension, net tension, which would be just across there. Okay, so I thought oh, this just gives the this wasn't on the other page. This just gives the formula for the group tear out. And what you're doing in each of these equations is you're finding the shear strength. So it's finding the failure that way, the failure that way, and the failure that way. And that's why this is in tension. That's the one on the end here. That one is that one, and then the other two are the sides. Okay, and this just shows an illustration of what those are describing. So this is the first scenario is the tension. That's probably the easiest one to calculate. This is just the tension of the wood, right? So you get that out of the supplement. It does have the factors, right? The adjustment factors on it, and then you just get a net, right? This is a net is just the area minus the area of the bolt of the holes, right? The area of the wood, I guess, minus the area of the holes. So that one's simple. This one, you've got the shear. This is in shear. You've got two lines of shear. You got the shear on that side, and the shear is that full length. It's not going through the bolt. It's going beside the bolt. So that would be that full length, which is, I guess, actually they take S minimum. I think S minimum was, I think it's based on that. The lesser of that distance or this distance. Okay, it's that spacing times that must be the number of them times the stretch. No, this is the number of them there. This is the thickness of the wood, of course, to get the area. So the spacing and the thickness of the wood. So that's area time. It's basically just the shear of that line. And then the group is that area again, right? That's what these are. It's divided by 2 because in this case, I think they're considering, actually in the top, in that one too, they consider the bolts don't, the connectors don't all carry the same stress. There's a stress distribution of those as you go into the wood, and that's the same. I believe that's the same for steel. I think that's the way those group patterns work. And this averages it. It takes the average of those. Is why it divides by 2. Okay. All right. So that was all for the failure. 3 modes of failure on the connector, right? On the pattern. Well, it's actually the wood failing. Three modes of failure on the wood. And these are the modes of failure for the fastener. And what do we have here? My goodness, a lot of different modes of failure. First, it depends whether you've got double shear or single shear, so that's kind of nice. If you had single shear, you'd have to consider 1, 2, 3, 4, 5, 6 modes of failure, which means you've got to analyze each one of these and take the least of see which one controls. If you've got double shear, then there are 2 that would not apply, I guess, these 2. So you have those cases. And this, you can see what they're showing you here. This is the bearing, where it's, the bearing there. Depends on, that's why there are 2 different equations, whether the top is in bearing or the bottom is in bearing, whether it twists and you get bearing surfaces like that, whether the nail bends, whether it bends on the bottom, bends on the top. They're assuming here that you have different thicknesses for the top and bottom, or the sides and the middle. If you have the same thickness, then this simplifies a little bit. Then I think some of your ratios, some of these ratio numbers go to 1, and it simplifies when you do it, but still a lot of cases. And you can see that's what they're describing, are those different scenarios, different modes of failure for the fastener itself. Okay, so this is, so you've got to analyze all those, what we have 3 different modes of failure for the wood. Now you've got whatever 6 different modes of failure for the fastener, and then you compare them, right? And you've got to take the least overall. So I guess you could do the least of the first and the least of the second, and then you got to compare the 2 and decide what is the least of the least, and that would be the one that controls. So it does get to be a little bit of a calculation. Fortunately, in practice, it's a lot easier if you find the right numbers in the tables. But like anything, there's situations where you won't find what you're doing is not in any of the tables, for some reason, and then you're on your own. Then you got to calculate. Or what's also maybe harder to see in the tables, I don't know, maybe it's not that hard to see in the tables, is to optimize it. If say you pick one and you think, oh wow, that's not, it has a large reduction factor on. Where do you go from there? Sometimes that's easier to see with the equations, but maybe also, I guess in the tables you can also see the numbers vary. Okay, so I believe this is an example. This is an example that came out of the APA, or AWC, the NDS, has a book of examples, and I think I got this a few years ago out of the book of examples here. At any rate, it has very nice illustrations, so I didn't draw those. They must have come out of here somewhere. But this book of examples is a kind of handy thing, because you can kind of check yourself on some of the more complex calculations that are in the NDS, and it gives you an example. There are examples of simple beam design, there are examples of column design, and then there are also eventually examples of some connections, I think. So that's a handy reference to have. Okay, so this example, what do we got? 10 minutes? Do you think we can get through this in 10 minutes? Well, we'll see. If we don't quite finish it, maybe we'll get through the first 3 scenarios, and then we can compare the bolt strength later. This is a splice like this. It was supposed to be like this example. That's why I brought this up here. Basically, with a plate in the middle and 2 on each side. These are 2x12s, so my little 2x4s are a little on the small side. The 2x12s are a lot bigger. We're going to do this with live load. Just like with steel, you have to oversize the holes. So although we're using fairly large bolts, 1-inch bolts, my gosh, that'd be big for steel. Usually you just got 3/4. I don't know. Okay, somehow they are using 1-inch bolts. And so our hole size is a 1/16 over. So we've got to reduce, when we find that net area, it's going to be taking that out. We do have, if you remember, that was 7D was the end distance, right, that they like you to use. We do achieve it there, but not here, not on this middle one. This is only, to the center, it's only 4, right? So we'll have to look at a reduction factor with that end distance. So, okay, and I guess in the end what we're looking for is the capacity. All right, so here we go. We'll look first at the wood. Those were those 3 different failure modes with the wood. And this is coming out of that Appendix E is where those equations are. So let me see if we got all these things. This is the simple equation. This was the easiest one. This is the section tension capacity. So it's just tearing across here. So really all you have to do is find that area. It's a tensile strength of the wood. Okay, so you have to put the factors on it for tension, and the net area of the wood. So you've got the area of a 2x12. What is the area? I mean, it should be pretty easy to figure out here. Oops. If I can find the area of a 2x12. Okay, 2x12, it says 16.88. So this should be 16.88 is the 2x12, right? That's our minus the holes. And there are 2 holes, right? We got 2 of them. They are 1 inch and a 1/16, right? So that'll be 2 times. Is that 1 inch and a 1/16? I hope. 1 inch and a 6. That's supposed to be 2.5 there. 1.25 inches times the thickness, right? 1.5 inches. So that is a hole. That's the that's 1 hole. And this is, there are 2 of them. So if I subtract that, I should come back to that 13.7. So that's my A net there. Man, I'm going to have to buy a new pen. It can't be, it's always going crazy. Okay, so that, you simply, here we have the tensile strength out of the NDS. This must be, oh yes, Southern Pine. We've hardly done any with Southern Pine. Southern Pine, that's because there's not too much Southern Pine up here. I don't know why we don't have too much Southern Pine, but Southern Pine has a table all its own in the supplement, which incorporates all the other factors. So we don't have to do, what is it, CF is built into this. Well, I guess that's probably the only one. But still, hey, you don't have to look up CF. But you do have to look up the size. So it gives it for a 2x12 down here. 2x12s, number 2, 450 in tension. Okay, so there's that 450 in tension. This is the live load factor. We got that, and that times the area. So there it is. Okay, that one, piece of cake. 7,000. We should keep track of these. This is E2, huh? E-2, is that how it? No, E.2. Okay, and that is 7,706. 706. Okay, pounds. Okay, that's got that one. Next one. Here's the row tear out. Woo, okay, so there's the formula for the row tear out. That formula is based on these, but there are always 2 lines of shear for a row, right? You got 1 line there and a second line there. So that it gets multiplied by 2, which means these 2's cancel out, and you end up with, that's where this comes from. That's why there's no divide by 2 in that. Okay, so we've got to have the number of rows, the shear strength. So we look up the shear from the supplement, right, for the Southern Pine. Yep. And this is our factor for live load. Okay, so that gives us the shear stress, allowable shear stress. The thickness goes on here because we're getting the area here, right? That is the area. So the thickness is 1.5. We got that. S crit, I believe, is you either take the lesser of the end distance or this distance. And in this case, they're both 4 inches, right? So we'll use 4 inches. but I think you take one or the other. Here it says, is the minimum of the end distance in a row and the in-row bolt spacing. So right, it's exactly what I said. It's the minimum of those two. Okay, so we got that. We plug it all in, and apparently per row, for one row, it's got that value, and for both rows, it comes out to 7,875. So E3, 7,875. Okay, thanks. 875. Okay, so, that one's already higher. Amazing that they're that close. Okay, next. This guy. Group tear out. Okay, all right, so here we've got, this is the same equation that I had for shear back on the other page, except now I've only got single shear, right? It's only going down one side, so I have to leave that 2 in there. It doesn't get canceled out. This is that distance there, right? That's that guy, and this is supposedly 1, and this is the other one. They write it as 2 formulas because you might not have, I mean, potentially, if these were staggered, you might have 3 in one row and 2 in the next, and 3 and 2. So you might end up with 2 on that outer row, right? So that's why there are 2 formula. You have to, the first one and the second one, I guess. Here they call them first one and second one. Okay, and yeah, our hole size are a 1/16 over. Yeah, we said all that. So this is the area up here at the top. I guess this is the on center was 4 inches, wasn't it? I think maybe I should go back and look. Yeah, that's 4 inches. Okay, so, whoops, sorry. This was 4 inches. And so I'm taking 4 inches and I'm subtracting half a bolt hole there and half a bolt hole there. So it ends up subtracting a full bolt hole, right? And that, I won't write it out, but that's that area there. Okay, and we already got this from the other page. It should be the same. 3938. Let me see if that's what, yeah, that's what this was for one row. 3938. Okay, so, right. Okay, so we got that, and you put those together, right, and you end up with this. So 6418. Looks like the winner. Okay, so that would be the one that controls. Right, that'd be that guy. Okay, and the next part, maybe we'll put this off until... Oh, we can do this. This only takes a minute because I don't actually do the calculation. These are all the scenarios, right? These are all the equations, and I actually worked through each of these equations. This is double shear that we're talking about. And in double shear, we've got to look at all 4 of these scenarios, so, right? And I actually did calculate them out, but I didn't write it all out here. I did write out the one maybe that control, or I wrote out these values. This is a ratio. Yeah, oh wow. These ratios, the R's here, are down here. Ratio of the lengths, or ratios of the, this is main member and side member, main member and side member. Our main member and side member are the same in this example, so it's those ratios end up being 1. So that simplifies these a little bit, right? That gets rid of those guys, or they just become 1. Oh, yeah, that doesn't go away. It goes 1. Sorry. I shouldn't have done that. Yeah. Okay, that's 1. Okay, and oh, let's see, whatever. This is the thickness, apparently, of the main member and side member, and the strength in, oh gosh, where is that? Main member dowel bearing, the bearing strength of the wood. Okay, so you gotta get that. These K's, oh wow, that's a whole nother calculation. In, where do they show up? There. So that K, we need that K, so that's what that is. I calculated that apparently from all those. The factors are pretty, actually they're not that many variables, but there are a lot of combinations of them. This is the, for the bolt, this is the bolt here. Right, so that's a 45 KSI bolt apparently. All right, and you put it all in, and then you've got that, so that gives the Z for each of these. That's what I was calculating here, right? And this is the one that controlled the 2306, so that's what I've got here. And then you've got to put the, just like with before, you got to put the adjustment factors on it. This is the live load. CG is that pattern, right? This is the end spacing, which we're going to have to reduce because we've got 4-inch, which is only, yeah, is less. Let's see, I think it, or maybe I don't have exactly 4-inch. We'll see. Okay, and the temperature. So just looking at these, this is the formula, and I think actually I actually did do that by the formula and got that number. And then if you go to the table, this is side and main, so we'd be in that. This is side, so we'd be in square inches. That's the area. That's what we said was 16.88. So we're actually in there, right? Wasn't it 16.88? Was the area of the 2x12. Anyway, and the number of fasteners is 3, right? I got 3 in a row. Do I say that somewhere? I think that's what that is. So that should come down somewhere in here. So the table's actually giving me 99. I calculated 97. I guess that's within 2%, but okay, whatever. Somehow we didn't agree precisely. Okay, that's that. Here's the delta factor, the end distance requirement. We've got an end distance, I think, that was 4 inches, right? And they're saying here, which one am I supposed to be using? Softwoods. There we go. Tension, softwoods. I'm supposed to have 7, so that would be the 7 inches. This is based on the diameter. So they're saying, or 3.5. Well, I've got a little bit more than 3.5, so I could use this calculation down here. I've got 4, and I'm supposed to have 7, and I think it's that ratio, right? Is what I've actually got. I mean, it's based on area. I'm just taking the length, but it's times the same. The 1.5 inches divides out actually. So if I take that ratio, I think that's what that's probably equal to. Well, 4/7. Okay, is what that should be. So I increased it a little bit, but you can only increase it so much. So you multiply all those factors times the 23. This is on one. Let's see. Oh gosh. This was on all the bolts, right? Pounds least. Okay. Yeah, I think this was on the full pattern. So then I divided it. I divided it by the bolts, I believe, to end up with that bolt. How many bolts? I thought I had 3 bolts. Okay, well, somehow I have to go back and look at that. Divided that by the bolts to get the pounds per bolt. And the pounds per bolt, because that's what I've got over here, right? That's comparing it to that. And that comes out, oh, no, this is total. This is the total, total for the connection. So that then times the number of bolts, I'm sorry. I've got 6 in the pattern, right? 3 and 3. I had 2, 3 and 3. So this is times 6, right? 6 bolts. So that comes out to be 95.89. Okay, so the bolts. 95.89. Okay, so they're not controlling. That, all that just shows that that doesn't control. And you could get, should be able to get that number. I guess the number, oops. Oh, all right, I just lost my recording. I should get, be able to get that number out of this table. So, although this thing just went, okay, it must be time to end. Look at this. Up. Okay. Everything's going wacky here. I lost it. 1 inch and Southern Pine. Okay, and I think this must be, it's a little hard to read, but that must be the, not perpendicular, but parallel. That's parallel. Okay, so that comes down to 2310. And I had said 2306. Okay, so it's pretty close. The table value is 2310. So you could, and that includes all 4 of the different failure modes, right? So this table is pretty valuable table. This is double shear. It gives you, you've got to match this 1.5 and 1.5, and the bolt thickness, we got that. Okay, and then this, that gives you, that solves all, what was it, 4 of the, in our case was 4 equations with double shear, which are pretty complex equations. So it's a lot simpler with the table, but at least that came close to what I got. I must have been off maybe a little bit here, I don't know, somewhere. Wherever. Or no, that's not even in the equation. That's still multiplied on in the end. Okay, right, so the conclusion of the whole thing was, that's the strength. 6,400 pounds. 6,400. All right. Whew. But we're not going to do that. That would have been the homework problem, but not this year. Maybe next year. We'll see. All right. Good enough. Do give some thought. Oh, you know what? I should post that sign up. I think I did post that sign up, didn't I? Did anybody look at it?
Yes.
Have you? You did. Did you sign up? You did. Oh wow. Okay, I better look at it. Oh, good. You should sign up for a time because that's just it's a week after next, right? That we're going to do those. Next week we'll finish up this on Tuesday, and we'll figure out what to do on Thursday. And then the next week, we'll be doing those. So you know what you're doing. You're doing the flitch beam. You know what you're doing? Oh, you are? Oh, excellent. Okay, flitch beams. And we can set up that, when you get it made, I'll go down today and start to look at my dusty testing machine down there. And you guys are doing the bridge, right? Okay, so you're in good shape. Okay, the people that are here know what they're doing. I don't know about everybody else. We'll find out. Okay, good enough. Have a good weekend.